Assalamualaikum and hello everybody. Welcome back to KNC 2123. This is still steady state heat conduction, part B, second part that is on fin surfaces. But in this video, you're going to look at some examples related to these fin surfaces. Okay, so the first one. Okay, you can look at the Chanel book that I recommended. Okay, this is probably second edition, or this number probably from second edition or third, but they're still in the same book, right? They still have this book in the latest edition. Now, consider a very long rectangular fin attached to a flat surface such that the temperature at the end of the fin is essentially that of the surrounding air. All right, so by looking at this, you already know what type of case is this. If you remember from the previous video, there are 4 cases. Okay, so the first one is a very long fin, right? The second one is adiabatic tip, the adiabatic tip of the fin, and then the third one would be specified temperature at the tip of the fin, and then finally convection from the fin tip. Okay, so which one do you think this case is? Right. So it says here that the fin tip is the same temperature of the surrounding air. So this means the fin has a very long, the fin is very long. Okay, it's very long that it's very long that so for example, you have this fin, right? And then you can plot the temperature profile. So this is the length of the fin. So the temperature at this side, when you plot it, if you remember, it goes down to the ambient temperature, right? So it's very long that it can reach this temperature, okay? So in this case, this temperature is 20 degrees, right? So, okay, so it's given here the width and the thickness, the dimension of the fin, and then the property of the fin, right? And then the best temperature. So this is at the beginning here. This is at the best temperature. Okay, so estimate the fin temperature at the distance 5 centimeters. So it wants you first to find. This is the first thing that you have to find, the fin temperature at a given distance from the base, and the rate of heat loss. Rate of heat loss. So this is the second one. Okay. Right. So now you know what you have to find. Then, okay, you can illustrate by yourself like this. So you say that TB here is equal to 40 degree, and T at the tip here, and L here is equal to 20 degree. Okay, so when we talk about fin temperature, if you want to find temperature at any point on this fin, so you must have this temperature profile, isn't it? Temperature profile, temperature in terms of as a function of distance, right? So how do you get this? Right. So how do you get this? Is you can refer back to the slide. This is given in this equation. So you look for the infinitely long fin, very long fin, the first case, and you can find that. Okay, so the first thing, this equation. All right. So you have to solve this. So this is known, right? Or these two temperatures are known, and then x is 5 centimeter. So because you want to know the distance at x, right? So this is what you want to find, okay? And then m. So how do you find m? M is given by, you can call square root, isn't it, of HP over KAC, right? H is given here, heat transfer coefficient, okay? H is given. P is the perimeter. So how do you find P? So it's stated here, you see, it's a rectangular here, right? So this is 5 centimeter, and the thickness is 1 millimeter. So the perimeter is these two sides, 1 millimeter plus 1 millimeter plus 5 centimeter, 5 centimeter. Okay, so you got this. And this, what about this? The cross-section area, right? So this cross-section area, this is not the area of the surface, right? This is not the area of the surface. This is the cross-section area. So cross-section area is 5 centimeter times 1 millimeter. Okay. So you got this, and then K is also given to you, right? So you can solve for Tx. T at 5, you see here 5 centimeter is equal to, so you would find it at 29.8 degrees Celsius. Highlight the answer. All right. So usually, in this case, because of this, you will convert this later on to meter, right? Both this to meter, and you will find that you will have to use up to one significant figure. One significant figure. That's why you need your answer in one significant figure. Okay. Now for the second one is the rate of heat loss. So still, you refer to the slide and you will see the equation, right? The equation given is Q right. So this is known, and then you have all this, right? It's the same. You have all this. So you will plug it in, and then you will get 2.9 watts. Right? It's that simple. Okay, it will be as simple as applying this equation if you know what case is it. So you have to in your answer later on, I want you to discuss first how do you choose this equation, right? So you're going to see, for example, because the fin tip is at the surrounding temperature, it can be assumed that it is a very long fin. Okay, it's a very long fin because we only have 4 cases. Okay, the first one is it is very long. The second one is talk about there is no heat loss at the fin, and then the third case, you have to have or you have to know the temperature at the fin tip, whereas at the fourth one, you will have to know the rate of heat from the fin tip. Okay, so if it's not given, then you can choose either of the others. All right. Okay. Right. I hope this is clear. So let's clear this and go for the next one. Okay. Let's read this. All right. So if you understand how is this case related to fin? Okay. Let's illustrate this. So you have like a boiling water, right? I have a boiling water. Then you have a spoon. This is very so supposedly this is straight spoon. Okay. Okay. So this is very hot. Okay, very hot. So the temperature of the spoon, the part of the spoon submerged in the boiling water must be the same, isn't it? They must at one time reach equilibrium, so they are at the same temperature. Okay. So the ones extended outside of the water is actually acting like a fin. If you see, this is like the surface. Okay, this is the whole this water here is the surface, and the extended this part of the spoon is actually the fin to the surface. It's acting like a fin to the surface, where it conducted heat through it and release it from its surface. Okay. So that's why if you're putting metal spoon, for example, it's gonna conduct better heat, and your water is gonna be colder quicker, right? Rather than when you're using plastic, for example. Okay, so now what case is this? So this is the first thing that you have to know. Oh, okay, before that, as usual, we have to find out what the question wants, right? Determine the temperature difference across the exposed surface of the spoon. Temperature difference across the exposed surface of the spoon, which means it wants you to find delta T. That is temperature at the base here minus temperature at the tip. Right. So this can be assumed as the temperature at the base. So this is temperature at the tip. Okay. Now you have to discuss first how are you going to do this. So we're gonna make assumptions. So actually, for the others, all of the other problem if you read from the book, they start with assumptions, right? Assumptions. So you should make assumptions as well. So this assumption mostly applied to all problems in this chapter, right? In steady state heat conduction chapter. Okay. So we can say the temperature varies in axial direction only. Okay. So the first one, temperature. So in your answer, I want you to write it in full, right? Right, temperature varies in axial direction only. So what do you mean by the axial direction only? So if we take the spoon as a horizontal like this, right? So and take this axis, right? This is y, this is x. So this going this x direction is radial, isn't it? Yes, it's radial. And this is axial. Okay. Right. So we're gonna take it one dimension only. Okay. And then so this is we can say is steady state, isn't it? Steady heat conduction, of course. In order for you to be able to use this analysis, is that it must be steady heat conduction, right? And then we can say that the thermal properties and the heat transfer coefficient, right? Or we can say H, okay, heat transfer coefficient are constant, okay, constant throughout the change of the temperature, even though the temperature change, but we can say it is constant because this is sufficient for our analysis, right? The temperature might not be too high that it changed the thermal properties, okay? So the average could be taken as constant, okay? And then we can say either you can say radiation is neglected, or if you want to say, if you want to take into account, you can say the heat transfer coefficient already includes the radiation, which means that you don't have to do radiation separately anymore because it's already been taken into account in this value here. Okay, so this is just to make this problem as real as possible. Okay, and as simple as possible. Okay. Now, the last thing that you should write is what? The condition of this. Now, the first one is talking about the infinitely long fin, right? Whereas in this case, it didn't say it is the, okay, it says here 7" in the A. So this is 7" in the A. And So this could be, and you see that it is very long compared to the cross section, or to the diameter, okay, or the width of this of the spoon. So it could be the first case as well. Okay, so case number 1 is okay, and then this is also possible, but it didn't say that the temperature at the tip is that of the surrounding, right? Because you know that a requirement for a very long fin is that the tip of the temperature is the temperature at the tip is the same with the environment, right? So yeah, probably we can keep this KIV, right? What about case number 2? So case number 2, it didn't say anything about any heat, isn't it, lost to the from the tip, but that can also be taken into account because we're just going to take the Q equal to 0 at the tip, right? So case number 2 is usually mostly possible, right? What about case number 3, right? This is KIV, this is possible. What about case number 3? Case number 3, of course not. There's no temperature at all stated, isn't it, for the tip. So case number 3, no. What about case number 4? There's no also stated how much heat convection to the tip, right? So you can use either of these, but it is safer to use this because it did not say here that the temperature at the tip is that of the surrounding, okay? So it's safer for you to use the second case, okay? Now, so in order for you to find this, right? Okay, so you're right. All right, and then you know that you have to find the temperature at the tip, right? So yeah, of course, this is not, because you don't have the temperature at the tip. Okay, now TV is known, okay? So how do you find temperature at the tip? Is from temperature profile. Okay, so you look back in the slide and look for the second case, and you will find that the temperature profile for adiabatic fin tip is given by this. All right, so L here is equal to X here is equal to L because you're looking at the tip, right? So this could be 0, right? So when this is 0, this cos here is 1 here. All right, so now you have to find M. So M is the same equation as we seen before, HP over KAC. All right, so H is given. We're talking about P letter. K is given. Okay, now P. So how do you find P? Yes, so you see it here, right, from here, isn't it? So 2 times this one plus 2 times this one, right? This is 2 sides this plus 2 sides this. And then AC is just this times this, isn't it? The cross-section area. Okay. So finally, you will find TL, or you can put in 7 inch here. So you have to remember to change all the units, and then you will find TL to be 75.4 Fahrenheit. Okay. So your delta T, you plug in, you will get 124.6 Fahrenheit. So this is your answer. All right. So let's clear this and look at the other. Now the third one. Let's read this before we do it. Okay. So the condition here, the situation here that we have, okay. Okay, now first you have to determine what the question wants, right? Determine the rate of heat transfer from the surface for a 1 times 1 intersection. Also, determine the overall effectiveness. You have to highlight this. So remember, so this one is Q. So this is number 1. So the second one that they want is effectiveness. Not efficiency, right? Effectiveness. Okay, so how do you do this? All right, for number 1, so the Q, the Q total here is equal to Q fin plus Q unfin, if you can remember. So Q released from all of these fins plus Q released from the surface that has no fins. Okay. So let's take a look at Q fin. So this is given by so this is the efficiency of the fin times the maximum that it can remove. Okay, so this is given by, okay, let's take a look at this one first. How do you find the efficiency of the fin? Now you have to see this what is the type of the fin. Okay, this is like cylindrical fin. Okay, so because it's cylindrical, if you look back at the slide, this is given by this equation, down ml over ml. Okay, so from here, how do you need to find m, isn't it? How about L? L is given to you. Is L given to you? Yes, 2 centimeter long. Now M is HP over KAC. right? So H is given. So P is perimeter here. So how do you find perimeter for this? You have to remember yourself. K is given, and then AC is just this area, the cross-section area of the fin. Okay, because we're talking about fin now. Okay, so you can solve this. You can solve it, and I want you to find a way on how to use your calculator to calculate a hyperbolic function. Okay, all right. So this second term here. So how do you find this? This is given by H A fin. So this is area of all fins times the temperature difference between the surrounding and the base temperature, right? So the surrounding is given here, and the base temperature is this, right? So at this surface temperature here is the base temperature, and H you already have. Now, area of the fin is given by the number of fins times area of each fin. Okay. So the area of each fin is, if you see, area here, right, plus the lateral area here of the cylinder. Okay. So that's this area. But how do you find how many fins? Now you have to illustrate this, right? Let's take a look at this. It says here, with center to center distance of 0.6 centimeter. Center to center. So center to center. So this is 0.6 centimeter. This is 0.6 centimeter. So each of this is a fin, okay? So you have a square of 1 meter times 1 meter, right? So how are you going to fit in this distance here in this area? So you can just take this as a square, right? As a square like this. So how many squares you can fit into this? So take this area here, and then take this area, right? You will, and then you divide it, isn't it? And then if you see in this square, it's actually this is going to be quarter of the fin, right? Because it's a circle like this, right? When you cut it like this, it's quarter, and when you add up, it's actually 1 fin. So 1 square here is actually 1 fin, right? So that's why you can just take this divide by this area. So n here, n is 1 meter square divided by times 0.006. So you will get n equal to 27,777 fins. Okay, you put it in here, and then you put in your value of your area of each of the fin. You get total area of the fin, and then you put in H and temperature difference. You get the maximum heat that can be released by the fin. Okay, and then times with the efficiency of the fin. Okay, that you calculate using this. So this is from the fin only. Now this one, the unfin area. So the unfin area is given by HA unfin times the temperature difference. Okay, so how do you calculate the unfilled area is, you can see this is a square, right? And then it's like as if you have holes of circles here. So you have to deduct this area from this. So it's going to be it's going to be 1 meter square minus 27,777 times area of this only, okay? Circle area here, right? Pi, okay? Plug it in all, and then you will get the total Q. So total Q, you will get about 17.4 kilowatt. All right, so this is number one. So number two is the effectiveness. So this is given by Q fin divided by Q no fin. So Q fin you must use here is the total here, right? So okay, let's right. Of course, because you want to see the performance with the fin over the performance without the fin. When I say performance means how much heat it can be released or it can remove. Okay. So for without the fin here, so it's merely HA no fin times the temperature difference. Okay, so this area is only 1 meter squared only, right? So you plug it in, you will get about 7.1. Okay, so that's your answer for B. Okay, let's clear this and move to the next one. All right, so this is the last example for this video. I want to read it. I want you guys to read it before we do it. All right, so this question wants you to find the rate of heat loss from the pipe. Now, I want you to think what condition is this? So you have to familiarize yourself with several conditions that you've learned from the previous video. If you can recall, table 3.7, there are complex geometries, right, involving or that can be reduced to fin problem, or it can be approximated to fins, right? So In this case, if you see this figure, you can see the first case in table 3.7, right? You must determine first that L is far larger than D, right? You see 30 meter compared to 10 centimeter. So this is the first criteria. L here is very large compared to D, and then Z is also 1.5 times the Z here is it must be larger than 1.5 times the diameter. If you times it, you see it's more than sufficient. So this ground here can actually act like a fin to this because of this geometry. Okay, so that's why you can use the conduction shape factor, right? Conduction shape factor. If you remember, the equation is simply SK T1 minus T2, right? This is the general equation for the conduction shape factor, the equation to calculate heat transfer by conduction. So you have to write down all the assumption, right? So it is steady state, so the properties are constant, right? And then you can say that it can be approximated to fin surfaces, right? Or say complex fin surfaces, right? And then because Z is larger than 1.5 the diameter, and L is very large compared to D. Okay. Now you have to find S. S is from the first case, isn't it? So S is given by 2 pi L over ln 4Z over D. So in this case, because this is a generalized case, all these parameters here, you have to refer to the table. Okay, you have to refer to table 3.7, which one is L, which one is Z, which one is D. Right? In this case, it's already given here as well. Okay, so all of this you have this. So you get S equal to 62.9 meter. And what about T1 and T2? Which one are you going to use? So of course it's going from hot to cold, right? So T1 is hot, T2 is colder. So you got this, and then K is also given to you. And don't forget about the units. You have to synchronize the units. Then you will get Q equal to 3,963 watts. Right. So it's gonna be simple if you can actually approximate it to any cases in table 3.7, right? So I want you to read all the cases inside table 3.7, and then you can understand, and you can. So when you found a question like this, you can know which one to use. All right. Okay. As for your attendance, I want you to answer this. So from table 3.7, choose any state, right? The numbers of the case that involve buried materials, right, in underground. Okay, so you state whether it is case number 1 or case number 1, 2, 6, or 7, right? So I want you to indicate the number of the case, not how many. I want you to indicate the number written in the table there in 2.7, refer to the slide, which actually involving buried materials underground. Okay, so that's all for this video. So if you don't understand, please comment or you can contact me directly. And thank you.